Hi guys. Today let's talk about some math that we can use with gas problems. The first type of problem that we might find is one that we need the combined gas law for. So you can see that the equation of the combined gas law is here. P1 V1 T2 is equal to P2 V2 T1. And of course, P stands for pressure, which can have units of kPa or kilopascals, or possibly ATM, which is atmospheres. Volume for these problems can be in the unit of milliliters or liters, but temperature should always be in the unit Kelvin. And if you are given degrees Celsius, just change it to Kelvin by adding 273. Now, understanding that these units always refer to these specific variables will be really helpful and can identify what the givens are from a problem. The ones refer to the initial conditions, and the twos refer to the final conditions. So let's take a look at this first example here. A 5.00 liter air sample has a pressure of 107 kPa at a temperature of 223 Kelvin. If the pressure is raised to 129 kPa and the volume expands to 7.00 liters, what will the new temperature be? So the first thing I'm going to do is list my givens. The first given that I have is 5.00 liters. Now, because this has a unit of liters, that tells me that this is a volume. More specifically, this is volume 1, my initial volume, 5.00 liters. Our next given is a pressure, specifically P1 or pressure 1, 107 kPa. Next, we have a temperature, or T1, our initial temperature, 223 Kelvin. And again, by recognizing the units, that can help me identify the variables. Then we're told that pressure is raised to 129 kPa. So we have P2, 129 kPa, final volume. And the volume expands to 7.00 liters. So this is our final volume, This is our final pressure. So V2 is 7.00 liters. And we want to know, what is the new temperature going to be? So we are ultimately going to be solving for T2. What is that final temperature? Now, our base equation for this problem, since it is a combined gas law problem, we have an initial set of conditions and a final set of conditions with one missing. The base equation is as written. P1 V1 T2 is P2 V2 T1. Now, since I am solving for T2, that is the thing that I want all by its lonesome on one side of the equation. So to make sure that T2 is by himself, I'm going to divide out P1 and V1 from both sides. And that leaves me with an equation. T2 is equal to P2 V2 T1 divided by P1 V1. So let's plug in our values. So P2 is 129 kPa times V2, 7.00 liters, times T1. So it will be really important that you pay attention to which one you're plugging in. So this is T1, which was 223 Kelvin. divided by P1, 107 kPa, times V1, 5.00 liters. Now, before we actually do the math, we can take a look at the units and make sure that they work out. So we have kPa on the top and the bottom, which means ultimately kilopascals will cancel out. We also have liters on the top and the bottom, which means that liters as well will cancel out. Therefore, the only unit we have left is Kelvin, which does make sense because we are solving for a temperature, and Kelvin is the unit that my temperature should be in. So by looking at our units and seeing that they work out to a unit that makes sense for what we're solving for, I can save myself some time, because if my units don't work out, it means I've set up my problem somehow incorrectly. But they do, so we can continue to solve. So I'm going to multiply the top row together first. So 129 times 7.00 times 223. Very large number there, as expected. So then I'm going to multiply my bottom row together, 107 times 5.00, 535. So now I'm going to divide. $376.39, lots of decimal places. Our final step will be to round our answer to the appropriate number of sig figs. Since we're multiplying and dividing, we want to go back to our givens and look for who has the smallest number of sig figs. Well, in this particular problem, everything has 3 sig figs, because trailing zeros at the end of a number, are significant if there is a decimal point. So all of our givens have 3 sig figs, which means our final answer should match that and have 3 sig figs. So that gives me a final answer of 376 Kelvin. Let's look at another problem using the combined gas law. So 50.0 milliliters of a gas undergoes a change in temperature from 239 Kelvin to 303 Kelvin. We want to know what is the new volume. So 50.0 milliliters is our first volume. And again, I can recognize that as being a volume because milliliters is a unit of volume. So we're going to say V1 is 50.0 milliliters. Our next given is 293 Kelvin. Since Kelvin is a unit of temperature, this tells me that T1 is 293 Kelvin. And we rise to 303 Kelvin. So T2 is 303 Kelvin. So we need the new volume, or V2 is the unknown. Now here, we are not told anything about pressure. So we can assume that pressure is being held constant if we are not told anything about it. But that is okay, because one of the beautiful things about the combined gas law is if you don't have anything to plug in for one of these variables, you can completely remove it from the equation. So since I don't know anything about pressure in this example, I'm going to omit pressure from my equation. And then I'm going to be left with V1 T2 is equal to V2 T1. So if you're missing one, no problem. Just remove it from your equation and continue with what you do have. So here, this time I'm solving for V2. So I need V2 alone on this side of the equation. So I can divide out by T1 from both sides, which gives me the equation V1 times T2 divided by T1 is equal to V2. So now I'm going to plug in my values. So V1, 50.0 milliliters times T2, which is 303 Kelvin, divided by T1, 293 Kelvin. Now similarly, we can look at our units. Kelvin on the top, Kelvin on the bottom. They will cancel out. We'll be left with milliliters, which, since we are solving for a volume, is perfectly fine. That makes sense. Milliliters is a unit of volume. So let's calculate. So 50.0 times 303, fairly large number, divided by 293, so I can do my division now. So 51.706, lots of decimal places. So if we look at our sig figs, seems once again, we have 3 sig figs for all of our givens, because as I said before, trailing zeros at the end of a number are significant if there is a decimal. So 3 sig figs in every given means we're going to round our final answer to also have 3 sig figs, and that will leave us at 51.7 milliliters for a final answer. Which, if we think about the relationship between volume and temperature, they do have a direct relationship. So if temperature is rising, volume should also rise, and it did. Now, there are also times when we don't have 2 sets of conditions. We don't have a final or initial condition, in which case we can't use the combined gas law. But there is another that we can use. It's called the ideal gas law. Now, an ideal gas, in order to be ideal, I should say, requires that you adhere to all the postulates of kinetic molecular theory. But that is another video for another time. The mathematical representation of the ideal gas law is PV is equal to nRT. Now, our 2 new variables here are N, which stands for the amount of gas with the unit moles, and R, which is the gas constant. Now, one other difference here is that I need my volume to be expressed explicitly in the unit liters for this equation. So if given milliliters, we're going to have to convert to liters using our conversion factor. Now, the gas constant, there are 2 values of the gas constant. So when we choose which value to use, we have to look at what is our pressure unit given, and we should choose the one that has the same pressure unit because the gas constant R has this very large compound unit of either liters kilopascals over moles Kelvin or liters atmospheres over moles Kelvin. So the only difference between the two is the pressure unit that is involved. So we will want to match that to a pressure that is given. So let's look at a few examples. This first one here says, what volume will 0.400 moles of oxygen gas occupy at 298 Kelvin and a pressure of 52.7 kPa? So our first given is 0.400 moles, and this is that new variable N, and I can recognize that by the unit. The unit mole will always refer to the variable N. Next, we have our temperature of 298 Kelvin, and I can recognize that it is temperature by remembering that Kelvin is my unit of temperature. And a pressure of 52.7 kPa. That is our last given. Ultimately, we are trying to find the volume. So we are looking for V. Now, before I can use my ideal gas law equation, I'm going to have to choose my R value. My pressure unit in this problem is kPa, which means I want to choose my R value that also includes kPa. In this case, we're going to be using 8.31, this R value, because we have kPa in that unit. So since I'm solving for volume here, I'll take volume and make sure that it is by itself by dividing out pressure from both sides, leaving me with an equation: volume is equal to nRT over P. So I can plug in my values. N 0.400 moles times R 8.31 liters kilopascals over mole Kelvin times my temperature of 298 Kelvin. And all of that divided by the pressure, 52.7 kPa. So let's take a look at our units. Along this top of the equation, we're multiplying these three values together. When we do that, we have the unit moles here, and moles is on the bottom of the R unit. So when we multiply these two things together, moles will cancel out. In the same way, we have Kelvin is the unit here, and Kelvin is on the bottom of the R unit. So when we multiply these together, Kelvin will also cancel out. We have kilopascals at the top and kilopascals at the bottom. So kilopascals will cancel out. And this is why your pressure units need to match so that they will cancel out. So our only unit left is liters, which is perfect because that is a unit of volume. So we're ready to calculate. So 0.400 times 8.31 times 298. Now I can do my division. $18.796, a couple more decimal places. So once again, we'll look for sig figs. We have 3 sig figs in these givens. We also have 3 sig figs here. Leading zeros are not significant, but trailing zeros are if there's a decimal. So once again, we have 3 sig figs in all of our givens, so our final answer should also have 3 sig figs. So we will round to a final answer of 18.8 liters. Let's do one more example together. We have a container with a volume of 2.3 liters. So volume, 2.3 liters. It holds 0.500 moles of nitrogen gas. So 0.50 moles. That's going to be N, because moles is the unit of N. If the temperature of the gas is 298 Kelvin, so T, 298 Kelvin, we want to know what is the pressure. What is P? Now, we still need to pick an R value before we can calculate. However, since we're solving for pressure, it doesn't matter which R value I choose, but whatever one I choose will tell me what unit my answer will have. So let's pick this one this time. Let's use R is equal to 0.0821 liters atmospheres over mole Kelvin. Now we're solving for pressure. So I want pressure by itself. I can divide out volume from both sides and be left with an equation. Pressure is equal to nRT over V. So plug in my values now. N, 0.50 moles times the R we picked this time, 0.0821 liters atmospheres over moles Kelvin, times the temperature, 298 Kelvin, divided by the volume, 2.3 liters. Now, just like before, when we multiply these 3 values across the top, that means we're going to be multiplying moles by something where moles is on the bottom. So moles is going to cancel, and Kelvin will cancel for that same reason. And then we have liters up here and liters down there. So liters will cancel. So this time our answer is going to be expressed in the units ATM, which is an acceptable unit of pressure. So that is just fine. So we can calculate 0.50 times 0.0821 times 298. We can do our division now. 5.319. There's a couple more decimal places there. So when we look for sig figs, leading zeros are not significant. So we have 3 sig figs here, 3 sig figs here, but 2 sig figs here. Leading zeros aren't significant, but the trailing zeros are if there's a decimal. So here's 2 sig figs, and this is also 2 sig figs. So when in doubt, choose the smaller number of sig figs. That is the rule for multiplying and dividing. So 2 is less than 3, so our answer should be rounded to 2 sig figs, which gives us a final answer of 5.3 ATMs. Hope this was helpful. See you next time.